Hello everyone and welcome back to the Hardware City channel. I can tell you this feels so great, so please let me repeat this once again. Hello everyone and welcome back to the Hardware City channel. I took a look in my video history on YouTube and I found out that the last episode I made for this channel was just in October 2022. So it's only a little more than 3 years ago since I made the last episode. One could say there's a very big gap between the last episode and this one, but who cares? The truth is that I went through a lot of things, unpleasant challenges and obstacles in the past year, but in the end it turned out to be good, and I desperately wanted to go back again where I finished this channel and closed down the channel and deliberately restarted from scratch and providing new content, new things that are interesting, new physical effects I found out and things I can present to you, and hopefully give you some fun, some joy and some new technical insights with my projects. So, what are we going to do now? Today, this episode is dedicated to something I experimented with 2 or 3 years ago, which was a broadband receiver. I used this broadband receiver in a different context as I do now, but this is not important for this episode. A broadband receiver is something that works like a radio, but the difference is that a radio is deliberately tuned to only one channel, to only one radio station you want to listen at one time, and not many stations simultaneously. A broadband receiver is different because it starts receiving radio frequencies, let's say starting with the frequency F1 up to a frequency F2. And F1 and F2 can have a lot of distance in between. So that means essentially that the broadband receiver receives a lot of signals simultaneously. But this does not necessarily mean that everything, let's say, is overlaid, giving just a bunch of babbling voices you cannot identify anymore. In fact, it's a little bit different because radio propagation heavily is depending on environmental conditions like the weather, the season of the year, the time of the day. So you don't get everything at once. The reality is that some radio stations show up and by the time they become replaced by other radio stations. And intermix are a lot of interesting signals, like for example when someone uses a remote control for these remote power plug sockets people use very heavily in the household, or for example someone uses a smartphone to make a phone call. All these digital signals also become in some way decoded by a broadband receiver, and everything that gives noise and hum and that's the interference from electrical equipment. So there's a real world opening, and you can hear this more or less, I say more or less, or less at once. And it's like if you're looking at a landscape, no, and your eye is going over to all those details in the landscape, you can see, oh, there's a tree, there's a house, there's a river. And you can do the same with the ears when you have a lot of signals that come in simultaneously, and you say, oh, I can hear this, I can hear that. Oh, now I can hear my neighbor obviously is trying to make a phone call. Oh, now someone is using a remote control. It's an interesting experience to get all this at once, more or less. I think it's more fun than just listening to a single radio station with all the interference and fading you have in shortwave and medium wave reception. I think it's a lot of fun. And I made a circuit that is a very good compromise between simplicity, that means easy to make, and a good receiver performance. And I'm going to show you now how this works, and then in the next step how I made it. So do you remember this? This is my good old ICF SW7600GR, one of the best pocket all band all wave receiver that Sony ever made. And this is a receiver that, like I told you, is deliberately only tuned to one frequency at a time, so you can listen to a lot of single radio stations all across the world. What I made now is this, the black box. I think we need some more light here. Problem is that this box is so black that you can barely see it. But I will show you this in more detail in a minute. The difference between this receiver here and this one is obviously because you have no tuning knobs for the frequency. You have just one knob for the loudness. But the sound is very similar, so you can hear that it definitely can receive electromagnetic frequencies. The main reason why we cannot hear radio stations now is very obviously that this is a broadband receiver, and it catches also all the interfering signals coming from lots of electronic and electric equipment. So that means, for example, those LED lamps here at the top of my shack can cause interference, but the most source of interference is my PC, my computer. Especially when the monitors are running and we have a lot of electronic hum or even electronic mist coming out of my computer, and of course this blocks all the complete bandwidth of the receiver. But to give you an impression how what you can actually hear with this kind of receiver when you switch off your personal computer, I will show you now.
Norfolk, Anglia, dilettant s-a format ca istoric la University of London, School of Slavonic and East European Studies. Opera lui include cărți despre istoria politică a României în secolul 20, istoria comunismului, istoria serviciilor de informații.
Es lo que representa la Navidad mexicana en el Vaticano, el cual en su 17ª edición cuenta con la presencia del estado de Chihuahua, representado por su gobernador.
Okay, now we're going to take a look at the electronic schematic, and I will explain every detail to you. So this is the whole circuit, and you see it's very simple. It just contains two transistors, a diode, an integrated circuit which serves as a power amplifier, and some resistors and capacitors, nothing special, and an inductor, of course. So let's start with the inductor, because this is part of the HF front end, which more or less contains these parts here. I'm just encircling with my mouse. We have an antenna connected through the capacitor C1 just for decoupling purposes, injecting the energy from the antenna in L1. L1 turns the let's say current coming from the antenna into voltage, because it works like an impedance. As you know, inductors have an impedance that is non-linear. That means that they are more high impedant for higher frequencies than for lower frequencies. So that means that the impedance for higher radio frequencies is causing more voltage across the inductor, and lower frequency less voltage. So that makes the circuit basically more susceptible for higher radio frequencies. But this doesn't change the underlying principle. The key factor is that the HF energy, the amplitude modulated radio signal, is going through this Schottky barrier diode. Schottky barrier diode has a very, let's say, sharp characteristic, a current voltage characteristic, so it does all the modulation stuff. And the demodulated signal gets freed from any rest of the high frequency signals by this capacitor C4, which is short circuiting all the rest of the HF energy to ground, so that a more or less clean audio signal arrives here at the basis of the transistor Q1. Q1 is a standard emitter circuit. That means that it's biased via the network of R1 and D1. And this is also kind of regulation that provides a good stability for the bias of the diode itself. You can imagine if for some reason more current flows through D1 into the base of Q1, causing more current flowing through the collector of Q1, causing the voltage at R2 to go down. When the voltage goes down, then less current is flowing through R1 in the diode, so that the previous increase of the current of the diode is compensated by injecting less current, and that means a decrease of the current through R1. This is a network that stabilizes the bias of the diode at the, let's say, ideal point of demodulation. C2 and C3 are two capacitors to provide an AC ground for this circuit. The capacitor C2 for the higher frequencies and the capacitor C3 for the lower audio frequencies. So for both frequency areas we have a stable ground here for this regulation network. So basically at the collector of Q1 we get the demodulated signal. We feed the signal into the basis of the PNP preamplifier circuit Q2, and the preamplified voltage now is routed into the power amplifier LM386, which provides a signal that is high enough to drive a speaker or, let's say, earbuds or whatever you want to connect. The rest here is just eye candy, some filtering, basic filtering means to keep the voltage rail clean from any interferences with audio or radio frequencies, and also a green LED as an indicator for the circuit itself. So this is everything I can tell you about the circuit. If you want to convert this circuit into a, let's say, real radio circuit, then you would have to apply a parallel capacitor to L1 to make it a real LC circuit, just resonating on a single frequency and providing you with the ability to hear just one radio station at a time. This would have to be connected directly across L1.
Okay, now we're going to take a deep look in the inside, sorry. I already unscrewed these screws here. So we lift off the lid. That's better put it on this side because of the length of the cable. So here's some piece of foam. It's just to avoid microphonic effects between the speaker and the inductor. So you can see I followed a very simple approach and realized the whole circuit on a piece of wood with thumbnails or thumbtacks as let's say fixing points for the soldering. This is a standard 12-volt lead acid rechargeable battery, and here you can see the whole circuit. This is an inductor here. It's a very small one, just about 10 turns of enameled copper wire on a very small ferrite rod. Here are the both capacitors for the AC grounding I showed you. This is the diode here, the Schottky barrier diode. Here we have the coupling capacitor for the antenna. It's going through the BNC socket here at the top of the device. And here we have Q1, the transistor. This here is the resistor at the collector, and here we have the PNP transistor, preamplifier stage, and this here is the power amplifier LM386. Well, and that's all. You can see it's a very rigid design, because I could get all these aluminum cast housings for a very cheap price. Normally they're very expensive. And the only thing that remains to be shown is the top side. Wait. A bit different for me to handle if I have only one hand free, because the other hand is reserved for holding my smartphone. These are two sockets here for recharging the battery. This is an alternative output for the audio. This is a standard audio, what's it called, 3.5 millimeter audio jack with a switch, so that when you plug in some, let's say, headphones, and the speaker switched off and the signal is going through the headphone. And this is the antenna I showed you. Yes, regarding the antenna, you see I use this adapter here to connect a standard 4 millimeter this laboratory wire, or banana wire, banana plugs, and going through this little connector there on my shack. And from this connector I have a very small thin copper wire going through the outsides here out of my window, so I have let's say the antenna not in room but on the outside. This is because a lot of steel concrete is built into this, or was used by building this making this building, and you almost have any, or hardly have any, radio reception inside this room, because there's so much steel used for building the walls for some reason. And this works like a Faraday cage, so an antenna inside the room does not work very well. Okay, so the last take I have to make with my handy on a selfie stick, because normally I directly record my videos on my PC with the program OBS Studio, but what I want to show you now, the PC is really annoying, because it makes so much noise that covers everything I want to show you. Interesting thing, last interesting thought regarding the broadband receiver is that I found out that you can make, let's say, a very simple short range Morse transceiver with this circuit by use of a relay. Maybe you know that oscillating relays, and you can do a lot of things with oscillating relays. They are vibrating. That means you are wiring a relay in a way that the breaker circuit routes the current that goes through the solenoid of the relay, so that the relay is continuously interrupting its own power supply when it starts working. So that turns out into something like this. You can see here. This is just a relay that oscillates on itself. And the self-induction of the solenoid, every time when the current is interrupted, causes a huge spike and a rise in the voltage, a very short impulse that generates high frequency, let's say, interference. This is the noise you can hear on a radio. The interesting thing is, I have my Sony receiver here working, and if I switch on this relay, there's only a little noise, not much. But if I use my broadband receiver, you can hear it's mostly almost silent now. Now let's switch on the relay again. It's much louder. Why is it so? This is because, as I said, a normal radio is a narrowband receiver. It just operates with a bandwidth of some kilocycles, some kilohertz. And the broadband receiver has maybe a frequency range of some megahertz or even more. Because the interference that this relay here generates is broadband, because it's spread over the whole radio frequency band from the low bands to the high bands, that means also that the energy distribution is spread across all bands. So that means, as a logical conclusion, that a normal radio only catches a tiny little bit of this energy from the oscillating relay, and the broadband receiver, let's say, 1,000 times more. So the idea I have in my mind is to use the oscillating relay as a transmitter to, let's say, transmit signals in Morse code, or maybe by impulses of a specified length, to bridge some distance, let's say 10, 20, 50, maybe 100 meters, by putting a small wire as an antenna to the relay and using this broadband receiver as a receiver to receive the signals. So that could turn this whole circuit, by adding an oscillating relay, into a very simple, or maybe the simplest short-range broadband transceiver ever in the world. That would be a nice idea to follow in the future. But for now, I think it's enough. I hope after watching this first video that indicates the restart of the channel, you got some fun, some technical insights, maybe some new ideas to fuel your own projects. That would be very nice. See you again on this channel.